Okay, this is a video on combinations. So we've talked a lot about permutations already, and now we're moving on to a different type of arrangement called a combination. And so in problem 1 over here, we've got to form a group of 4 students. From a group of 4 students, we need to select president, vice president, secretary, and treasurer. So let's suppose that our 4 students are Abby, Bob, Carol, and David. And we could have, for example, president, we have our vice president, secretary, and treasurer. And so the president in one committee, well, that could be Abby, and then Bob, and Carol, and David. And then we could shuffle them around, and we could have, for the president, Bob, and then Carol, and then David, and Abby. Or we got Carol here, and then David, and then Abby, and then Bob, and so on. And there are a number of different arrangements that we could have here. I'm not going to go through each arrangement. However, in each arrangement, the order matters. So the order here of the positions matter, right? Because the first one, well, that's the president, and then the VP, and so on. Whereas in this scenario over here in problem 2, a committee of three must be selected from 4 students. So even though we have one fewer person on the committee, committee A, B, C with Abby, Bob, and Carol would be the same as this committee, would be the same as this committee, and so on, because it's just the same 3 people. Here, order does not matter. And so that's really the difference between a permutation and a combination. So in a permutation, the order is important, and because of that, there will be more possibilities. Example, the letters A, B, C have 6 different permutations, and there they are. So you have A, B, C, A, C, B, and so on. Whereas over here, the letters A, B, C arranged, A, B, C, I think I've done the same thing twice, C, B, A, etc., all represent the same combination of letters. So these are our committees with Amy, Bob, and Carol Carol, Bob, and Amy, or Abby, or whatever I said her name was. They're the same committee. So order is not important in a combination, and therefore there will be fewer possibilities. Our formulas for these, so this is the permutations formula that we've been working with. So we see n objects, and we're picking R among them. So, for example, in our committee of 4, we had 4 people, and we're picking all 4. And so that turns out to be 24 possible arrangements where order matters. And the order mattered because we had secretary, treasurer, vice president, president. Over here, the formula you can see looks very similar, where we have n factorial, we had that over here. And then we have n minus r factorial, we've got that as well. But in addition, we're dividing by r factorial. So here I had 4, and I'm going to choose 3. So the combinations button is found in the same place as the permutations button in our calculator. And it can be written like this, but another way that this is written is just in a set of brackets with a 4 above a 3. So you might see that in the assignment today, and that means a combination 4 choose 3. So in general, if I have n choose r, that can also be written like that. Okay. On this screen, we are to evaluate these combinations and make some conclusions. So if I apply the formula that we saw on the previous page, and that should also be on our formula sheet, we should see that 5 choose 3 will look like this. 5 factorial over 5 minus 3, n minus r, right, factorial, over r factorial, which is the 3. So if I reduce this a little bit, I would get 5 factorial. 5 minus 3, well, that's just 2. Oops. 2 factorial times 3 factorial. Whereas in the second one here, 5 choose 2, I have n factorial over n minus r, in this case r is 2, and then r factorial. And if I reduce that, I get 5 over 3 factorial and 2 factorial. And in each case, I can see that I end up with the same expression. I've got 5 factorial in the numerator, and then 2 and 3 factorial in the denominator, and same thing over here. So among 5 objects, choosing 3 and choosing 2 are the same combination. So this would be a good point for you to pause the video and try these two. Okay, what you should see here is a very similar thing, where we have n factorial, n minus r factorial, r factorial, and so this is going to be 10 over 7 factorial and 3 factorial. And in this combination over here, I've got 10 over 10 minus 7. Well, you can see that's going to become the 3. And then r factorial is the 7. Well, that's this guy here. So I end up with 10 factorial over 3 factorial, 7 factorial. And so I get the same value in each case. They're the same. So let's now turn our attention to a couple of examples where we have some situations where we're asked to determine how many different combinations there are. So here it says there are 10 types of ice cream at the store. Suzanne orders a cone with 3 different flavors. How many choices are there? So what this is basically saying is that a vanilla, strawberry, chocolate cone would be the same as say a chocolate, vanilla, strawberry cone. So all I do is put these into my formula. 10 choose 3, or remember, I can see that written this way, and it means the same thing. And if I put that into my calculator, I end up getting 120. All right, here's another example. A reading club must have 1 teacher and 10 students. If there are 6 teachers to choose from and 21 students, how many possibilities are there? So how many combinations for reading clubs are there? Notice here that we have the word and. So when we see that word, that's going to tell me to multiply. So 6, choose 1, right? We're choosing 1 teacher out of that group of 6, times, the and again tells me to times, 21 choose 10. We're choosing 10 students. So 6 choose 1 is 6. That kind of makes sense. And 21 choose 10. Well, that's a lot more possible combinations. 352,716. And so if I multiply those out, I get 2,116,296. Okay. This might be another point to pause the video and try this one yourself. Read through and think about what to do here in part A and B. All right, hopefully you gave that a shot and tried to figure out how to enter the combinations into your calculator. A company wants to hire 5 people to fill 5 positions that are identical. There are 12 candidates. How many ways can these be filled? Well, that's simply 12, choose 5. And remember, I could write it like this. And in my calculator, if I pop that in there, I get 792. So 792 ways those positions can be filled. The company wants to hire candidate A and 4 others. So that means there's really 4 positions to be filled. So for candidate A, I have 1 person. I choose that 1 person. That's just 1. And I times that by, remember, and means times, 4 others. And I believe I only have 11 left to choose from. So 11, choose 4. And that is 330. So there are 330 ways to fill these 4 positions and hiring candidate A. So looking at some more problems. This one, 7 women and 5 men applied for 4 positions at a company. The boss wants to hire at least 1 woman. How many ways can these positions be filled? So when we're looking at least 1 woman or at least scenarios, that means we would have, for example, 1 woman and there are 4 positions, so 4 men. Right, so that's 1 scenario. Or it could be 2 women and 2 men. Or it could be 3 women and 1 man. And the last possibility would just be all the female candidates. So at this point, maybe try and figure out for combinations of 1 woman and, remember what and means, 4 men. And how many combinations would there be in this case? Or means plus this case, plus the 3rd one, plus the final one of all women. All right, so in this case, the first scenario, 1 woman, so we're going to select from the 7 women, we're going to choose 1, times it by 5, choose 3, which is 7, which makes sense. 7, choose 1, there's 7 combinations. 5, choose 3, that's 10, so this is 70. Or means I add. And here, 7, choose 2, and 2 men is 5, choose 2, 5 men to choose from. And that gives me 21 times also 10. We saw this earlier that these were the same. 5 choose 3 and 5 choose 2 are the same. So plus 210. And our third combination, 7 choose 3 times 5 choose 1 is 35 times 5. And again, that makes logical sense. 5 choose 1, 5 combinations there. And so this is 175. We're going to add that up. And lastly, all women, 7 choose 4 times choosing none of the men. 5 choose 0. Well, that's just one way to choose none of them. And 35 ways here. So 35. We're going to add that up. And the total that I got is 490 possible ways to fill those positions. Here is a similar problem, and it says a math class has 10 boys and 12 girls, and just write that down, 10 boys, 12 girls. The teacher needs to make a committee of 3 students who will plan the curriculum for the semester. That sounds like fun. 3 students in a committee. Notice they don't have a particular role. So when there's no positions on the committee, then we know it's a combination. Versus when there are positions, then it's a permutation. Right. So we want to determine the number of committees possible given these different situations. So in the first case, it says there are no restrictions. So in that case, I just have a group of students, and there are 22 in total, and I just choose 3. And that turns out to be 1,540. And now, if there are no boys on the committee, so that means the group of 3 that I'm choosing comes exclusively from these 12 girls. So 12 choose 3, and we could even say 10 choose 0. This, whenever I choose 0, it's always just equal to 1, so it doesn't really change anything. But this would be 220. So there were 220 committees of no boys on the committee, so all girls. And now, if there is at least 1 boy, so that at least, we want to get used to seeing that and thinking about what that means. So that means I could have a committee of boy, girl, girl, boy, boy, girl, or all 3 boys. And in each case, I would have at least 1 boy. And so it's this, or that, or that. So remember, or means I have to add them up. So I'm going to have 10 boys choose 1. That's an ugly C. Let me do that again. 10 choose 1 times 12 girls choose 2. Or 10 choose 2 times 12 choose 1. Or, which means plus, 10 choose all 3. So this turns out to be 10 times 66, or 660, plus 45 times 12 is 540. And the last one, 10 choose 3, is 120. And so I add that other combination in, and the total that I get is 1,320. So this is the number of committees possible where there is at least 1 boy. All right, I think we'll look at this one with the cards last. And so in a standard 52 card deck, we're asked to determine the number of different 5 card hands. So your order doesn't matter. If I have 5 cards in my hand, the order of them is irrelevant. And so that's another thing to remember. A hand of cards, that's a combination versus a permutation. And same thing with the committee with no positions. That is a combination. There are no restrictions. All right, so out of those 52 cards, I'm going to choose 5, and this is going to give me a huge number of combinations, and that is 2,598,960. So quite a few. This hand includes exactly 2 jacks. So if you could envision separating the jacks out of the pile, I'd have a pile of 4 jacks, and I would choose 2 of them. And in my hand, from the remaining cards, so I take the 52 cards, I make a pile of jacks, that's where I pick these from, and then think about how many cards are in the other stack. If I separated into 4 here, I would have 48 left. And from those cards, which are not jacks, I'm going to choose the remaining 3 cards of my 5 card hand. So this is how I would figure that out. 4 choose 2 is 6 times 3 out of the 48 remaining cards. Well, that's 17,296, which leaves me with 103,776 possible 5 card hands with 2 jacks. And down here, I would like to add a word to this. The hand includes, let's say, exactly 3 red cards. So again, imagine envisioning that deck of 52 cards and we split into the red cards, and there's 26 of those, 13 hearts and 13 diamonds. And then there are 26 cards that are not red, and those are the black cards. So if I have exactly 3 red cards, I envision from those 26 choosing 3. And I need to choose 2 more to make up my 5-card hand. So I'm going to choose among the 26 black cards. And so that's 2600 times 325. And I get 845,000. And that is the number of hands with exactly 3 red cards. Down here, the hand includes at least 1 heart. So this one is considerably more work to add up all the different combinations here. So maybe this is a good point to pause and try that one out. All right, so hopefully you saw that you could have 1 heart and 4 others. Or you could have 2 hearts, or 3 hearts, or 4, or 5, and then the remaining here would be 3 others, right, to make up our 5-card hand, 2 others, 1 other, and here's 0 others. And each of these hands has at least 1 heart. So we want to look for that word, that phrase, at least, and that's going to help us to solve these problems. So think about how many hearts there are in the deck. Well, there's 13. In this case, I'm choosing 1. And then how many other cards are there that are not hearts? And that's how many I'm choosing 4 from. And hopefully you got that that was 39. It's the other 3 sets of, or suits rather, of 13. So this is one combination. Or, which means I'm going to add up the next combination, which is 13, choose 2 hearts, times 39, choose 3 others. Or 13, choose 3, times 39, choose 2. That's the case where I have 3 hearts. Next one, 13, choose 4. Down here, 13, choose 5. Times here, 39, we need 1 more to make a 5-card hand. Here, 39, choose none of them. And let's see. The total for the first scenario of 1 heart is 1,069,263. These are all really huge numbers. 712,842. This one, 211,926. And you can see as we become more specific, picking more out of a smaller group, that we end up with fewer combinations. Anyway, second last one, 27,885. And the last one, 1,287. And so if I add up all of these, right, this, or that, or this, or that one, or the last combination, I get 2,023,203. So, there you have it.